Okay, good afternoon, everyone. Welcome to another seminar of the Astronomy Department. Many thanks for joining us here or for following through our YouTube channel. Today, we are very pleased to have Professor Sara Buson from Würzburg University. Many thanks, Sara, for being here with us. And Professor Rodrigo Nemen from our institute is going to introduce Sara before her presentation. So please turn off your cameras and your microphones during the talk. And if you have any question, you can indicate this by raising your hand or by writing it down in the YouTube channel chat. So, well, the questions will be asked after the talk. So, Rodrigo, whenever you are ready, you can start.
Yes, absolutely. So today we are joined by Professor Sara Buson. So it's our great pleasure to host Sara virtually, unfortunately. And so Sara, she got her PhD from University of Padua, and then she remained for a postdoc in the University of Padua for 2 years. And afterwards, Professor Buson, she moved to NASA Goddard Space Flight Center in 2015 as an NPP fellow, as a NASA postdoctoral fellow, where she remained there until 2018. And since 2018, Professor Buson is a junior professor at the Julius Maximilians Universität Würzburg in Bavaria, Germany. And the field of work of Professor Buson is studying the high energy extreme accelerators associated with supermassive black holes in blazars. She has been using a variety of observatories to characterize and to investigate the properties of blazars, in particular the Fermi Large Area Telescope. And in 2017, Professor Buson, she was one of the key people behind a very important discovery in the field of black hole astronomy, where there was a neutrino emission detected simultaneously with electromagnetic emission from a gamma ray emitting blazars, the now famous Texas blazar in black hole astronomy. And I think Sara will tell us a bit more about this very important key discovery in the field of black hole astronomy. Sara, thank you very much for accepting our invitation, and the online floor is yours. You can share your screen.
Thank you very much, Rodrigo. Let me share the screen, and meanwhile, I would like to thank Professor Nemen for the invitation to join you today. It's a great pleasure for me to give this seminar and tell you a bit more about the science that I've been doing lately. The only regret, of course, is that I cannot be there, but hopefully we will be able to travel and I will come certainly to visit you there. I would like also to thank a lot Maria and Reinaldo, and as well Richard, because they made very easy my attendance here, providing all the useful information and the technical test needed to be here and present today. Okay, so let's go straight to the presentation now. The seminar of today is entitled Mapping Highly Energetic Messengers Throughout the Universe. And the title is deliberately taken from an ERC project that I was recently awarded a few months ago from the European Research Council. And this project will be focused on the study of these energetic messengers that we are able now to detect in our universe, thanks to many instruments. And I will tell you a bit more in the next slides. The roadmap for today's seminar is the following. I will first give a brief content of why we are very interested in studying this type of particles in our universe. And this goes back to a 100-year-old puzzle, that's the cosmic rays puzzle. I will then talk a bit more about the universe of gamma rays, especially active galactic nuclei, and a special focus on blazars among those. I will then introduce also the cosmic neutrinos, these new messengers that pretty recently we have been able to study, and now they are an important brick of the multi-messenger field. And finally, toward the end of my talk, I will try to provide a bit more content about the status of art in the cosmic messenger game, specifically focusing on the neutrino and gamma ray topics. I will just dedicate a couple of slides on the forthcoming decade, which will be very important, of course, for the students that likely are attending this seminar and will like to be involved as a major player in this field. So the first topic that I wanted to introduce today is the cosmic rays, these extremely energetic particles that populate our universe. Cosmic rays were first detected in 1917 by Victor Hess. And what struck already back then was the enormous power that resides in these particles. Just to give an idea, I put here the numbers in zeros of the power that resides in cosmic rays compared to the most energetic particle that we are capable to accelerate today in the most energetic accelerator that we have in our hands, and that's CERN. And you see that the energies that the cosmic rays can reach, they are still pretty far away from whatever instrument we can yet imagine to build on Earth. Nevertheless, we are able to detect this particle and learn a bit more about them. For instance, here, this is an historical spectrum that depicts the observation that have been taken so far, more or less, in the cosmic ray field. And we are able to already provide some insights on the origin of these cosmic rays. For instance, in the more or less lower energies from the GV, TV energy range, it's believed that the source of these cosmic rays is of galactic origin, for instance, supernova remnants or other sources. At the highest energies, which is exactly where the challenge resides nowadays, instead, we are still pretty lacking any evidence toward which could be the main contributors, the main origin for these rays. But we believe it's more likely to be an extragalactic population of sources. So just to point out that although these cosmic rays have been discovered since more than 100 years, today we are still left with a lot of open questions. How is the spectrum composed? How are they accelerated? And for instance, how are they propagated? And of course, what is eventually the sources that are capable of originating these extreme particles? To help in the case of the origin of cosmic rays, we can try to use other messengers, or what, in other words, other particles that are present in our universe and that we believe are created along with the cosmic rays. One of the main challenges in particular for the cosmic rays is the fact that they are charged particles, and as a matter of fact, by the time they are created in the distant source, and the time they reach us on Earth, they will have traveled a long path toward the universe, and they will be deflected, being charged by the magnetic fields, for instance, of the galaxy, the galactic magnetic fields, etc. Therefore, once we detect them, we cannot simply straight go back to the source and look to understand what source it was. On the other hand, this is not true for other particles, such as neutrinos and gamma rays. These particles are believed, as I will show in the next slides, to be originated in processes that origin also cosmic rays. And as a matter of fact, when they travel through the universe, they can travel almost unimpeded. This is true for sure for neutrinos, which once we detect a neutrino, we can almost be sure to just go back to the source and identify the status location where it was originated. Gamma rays we can play kind of similar game with one caveat, among others that I will mention later. And the main caveat is that these high energetic photons can undergo pair production with lower energy photons on the travel to Earth. And as a matter of fact, they may be absorbed in part, at least, depending on where they are originated. We will see a bit more about this. Another main driver to use in combination these different particles that we detect in our universe is an observational driver. And this comes from the observation of the energy density of cosmic rays. You can see in this plot over here, neutrinos and gamma rays. So when we plot, we take all the measurement that has been taken so far, and we plot that all together in the same plot like we have done here. What some scientists have suggested is that since they lie more or less at the same level, you see the energy content in these different channels is more or less the same, then they suggest that it's likely that there can be a common origin of these different particles. So all this motivates to use neutrinos and gamma rays together to help understanding what's the origin and different properties of cosmic rays. Regarding gamma rays, one of the main important instruments that is helping in this case today is the Fermi Large Area Telescope. It's a NASA observatory that has been put into orbit now since 2008. So it's more than a decade of observation that he has reached so far, and the main mechanism that it exploits to study gamma rays is the pair conversion process. So typically what will happen is that an energetic gamma ray will hit the top, let's say, of our detector. It will travel through the detector, and eventually in one of the layers, it will be converted, thanks to some converting material, into an electron-proton pair. Eventually, these pairs, as well as the cascades of particles that may originate along with them, will be recorded, and all the information will be downlinked on Earth, and then will be all processed in a way that we are able to recover the information regarding the incoming original gamma ray that was detected by the telescope. As mentioned, we have been doing this since quite some time now with the Fermi collaboration, and we are entering now the 13-year observations. And just to give you an idea of how the gamma ray sky looks like, here you have a gamma ray map that has been built with the first 8 years of observation, so 8-year photon map. And of course, the main feature that you can see by eye are these diffuse emission, and of course this coincides with our own galaxy. And another important feature that is clearly visible by eye are all these bright spots that are located farther out at high latitude. In total, we count now more than 5,000, more than 7,000 with the newer catalog actually sources detected confidently above 100 MeV. Just to give you an idea, this is a huge improvement with respect to the previous sky survey that was obtained with, for instance, Egret, where the team was able to detect at most about 100 sources. So now we are really able to do population studies in pretty deep ways. And one important thing that we have learned from this survey is that the sky at gamma rays is dominated by AGN of the blazar class. So AGN stands for active galactic nuclei. They are extragalactic sources. And before going into our multi-messenger story, let's also dig a bit deeper into this, explain a bit more what are active galactic nuclei. So typically, we refer to active galactic nucleus to the center of a galaxy. It's a special galaxy that hosts in their center a supermassive black hole. Typically, we are talking for the most massive black holes of masses of 10 to the 8, 10 to the 9 solar masses, just to give an idea. Given the peculiarity of the system, they usually exhibit very energetic phenomena. And the most important thing to remember regarding this type of sources is that the radiation cannot be attributed solely to star emission. That means that the nuclear fusion that typically powers the normal galaxies is not the main source of energy that is present in AGN. Among AGN, I would like to introduce also the fact that only 10% of them have been found to be radio loud, so they emit a significant portion of energy also in the radio band, and this is connected to the fact that we observed also some jets, so jets of relativistic plasma that are propagating from the center of the galaxy farther out in the universe. Another peculiar important characteristic to keep in mind about AGN is that they are broadband emitters, so they can emit radiation from the radio bands all the way up to gamma rays. Here is, for instance, one image of how a special galaxy like an AGN would look like. And you see that at the center is the center, so it's a pretty bright nucleus, and then these contours are highlighting the emission in the radio band. This emission actually is linked, as I was mentioning earlier, to the presence of relativistic jets of plasma. So what happens here is that there is a very efficient mechanism to convert the gravitational potential energy in electromagnetic emission. And this gives rise to this relativistic plasma material that is kicked out from the core and can reach distances pretty far out, up to the kiloparsec or even megaparsec scale in the universe. I will not describe too much the properties of this source, but I would like to just mention the fact that they are pretty asymmetric, as you see. And in particular, when we have the jet of plasma that is pointing straight to the line of sight, straight to Earth in our case, of course, what we will observe predominantly will be the emission, the radiation that is produced by the relativistic jet. These are a particular type of sources that are defined as blazars. Blazars have a typical spectral energy distribution that is characterized by two broad bands. As you can see here, this is a function of the flux energy flux, and here a function of energy. And you see that typically we observe one first peak located at lower energies, typically in the infrared soft X-rays band. And the higher energy peak is typically located in the MeV-GeV range, which, by the way, is where we are actually observing with the Fermi lat. Regarding the typical processes that we think are acting in blazars, there are different schools, different ideas. In particular, so far, let's say, it's been quite well understood nowadays that the lower energy peak is very likely described by synchrotron radio emission. So typically what we think is happening is that you have some electrons, for instance, in the jet that are accelerated. Since there is also a magnetic field, these electrons will spiral, and therefore they will create photons via synchrotron radio emission. Regarding the higher energy peak, there is still some debate between people, and there are different mechanisms that have been suggested in this regard. The most popular framework so far is the so-called leptonic scenario. So in the leptonic scenario, we have, again, the primary players are electrons. And what we believe is happening is that these primary electrons are interacting with lower energy photons that will be available anyway in the source, as we know, as a matter of fact. And eventually, there will be the process of inverse Compton scattering, which will create the gamma ray emission that we observe here at the highest energies. However, it's also reasonable to assume that along with the electrons that are accelerating the jet, there could be also some protons that gain energy. If protons gain energy, then this is typically described in the so-called hadronic scenario. In this case, we will have protons accelerated that will interact as well with other particles, and eventually they may create pions and gamma rays. If they create, for instance, pi zero, of course, we know those will eventually decay and create a couple of gamma ray photons. And this could easily explain, for instance, the high energy peak that we are observing in gamma rays. So I should say there is still no conclusive proof that this scenario or the other is the final one, the most promising one. And one particular interesting fact of the hadronic scenario is the following. Along with the pion, pi zero, of course, protons will also create pi plus, pi minus particles. And in this case, we know that eventually these particles will cascade down and create also neutrinos. So in the hadronic scenario, we do expect, along with the gamma rays, also the production at some extent of neutrinos. And this is particularly important because, of course, we do not expect that for the leptonic scenario. So to say it in other words, if we are able to detect a in an incontrovertible evidence of neutrino emission from one of these sources, then we can be 100% sure that the process that was originating it was an hadronic process. And in this case, hadronic process means that at some extent there were also heavy particles accelerated, and we go back to the cosmic ray framework idea. So this is very important. Understanding this process is very important when we want to use all the messengers, all the cosmic rays, neutrinos, and gamma rays together to try to understand the origin of these particles. Let me just mention the fact that for blazars of the type that Fermi is observing, the typical spectral energy distribution that we observe, implies that the neutrino emission should be picked around 1 PV, so from 100 TeV up to 10 PV. And this will become very, very important later when I will point out how we can detect neutrinos. Just to summarize a bit clearer the processes that we are talking about. So we have the hadronuclear process, that is what we just mentioned, in which heavy particles like protons can be accelerated and can create pions, which in turn will create both gamma rays and neutrinos. On the other hand, another process that can be acting in blazars is the photodronic process, where we have only gamma rays. Another way to produce hadrons is also the photodronic process, in which we can accelerate these particles, which eventually will decay in the main channel, which is the delta plus particle, and again will create gamma rays and neutrinos. So these are the main processes that could create also neutrinos along with the gamma rays. For the detection of gamma rays, however, it's not that straightforward to connect them with neutrinos and gamma rays. And the fact is very simple. It's related to the fact that gamma rays are not exclusively produced in hadronic processes. As we know, there are other processes, like for instance, Bremsstrahlung or in Compton, that can produce as well gamma rays, but do not require the presence of hadrons. So, as a take-home message, we can use gamma rays to study the origin of neutrinos and cosmic rays, but they are not to say the last word, because we will never be sure that they were exclusively produced along with the hadronic processes. So the trick, the power is using all the messengers together, as I was mentioning before. So trying to find a combination, or observations actually, that help us linking the origin of cosmic rays together with the origin also of the other particles. Because, as mentioned before, the other particles can travel straight to Earth, and they are more easy, let's say, to handle observational-wise. I mentioned about gamma rays earlier, and now, of course, we have to introduce neutrino observatories. And today, the most effective neutrino observatory is IceCube, which is a gigaton neutrino detector located in the South Pole. Now, I probably don't need to explain to you why people went to the South Pole and built such a huge experiment to detect neutrinos. Neutrinos are the most abundant particles in our universe, right? If we look to our thumb, in 1 second, we have 1 billion of neutrinos going through the thumb. But as you know very well, it's not that easy to detect neutrinos. As a matter of fact, if our body were to be a neutrino detector, we would record 1 collision of a neutrino with an atom of our body every 1,000 years. So, of course, we cannot really wait 1,000 years to do neutrino astronomy. Therefore, a way to get around that is to build a huge detector where we have a larger effective area, and we have better chances to get some more statistics regarding neutrinos. For this, among these reasons, there is why the IceCube Observatory was built in the South Pole. As mentioned, it's a 1 kilometer cube array. Here you have, for instance, the comparison with the Eiffel Tower, just to understand the size of the observatory. It's deeply buried under the South Pole. You see, this is only the observational, the offices, basically, the experimental house where the observatory is located down. It's composed by, at the moment, 86 strings, and the main way to detect the neutrinos is through the silicon light using photomultipliers. IceCube was completed in 2010, and since then it started also to take science data. Since then, we had already actually quite important results and discoveries thanks to IceCube. And this is, in my opinion, the first most important one, of course. Here, what we are looking at is the histogram of neutrino events detected by IceCube. The histograms, the color histograms, are highlighting the expected background. This is instead the actual measurement, and as you can see, more or less at low energies, one could maybe say that everything is consistent with the background. But the paper they published reported the discovery of these couple of points appear at higher energies, which were deviating a bit too much from the expected background. And this led actually to the discovery of a significant signal of cosmic neutrinos at the highest energies, which now, by the way, has been, of course, confirmed and also strengthened in detection, thanks to the newer data. Let me simply summarize the status of art, because of course there is a lot of science that has been done thanks to IceCube, but for what we are mostly interested in now is the fact that we are confident that at the highest energies we are detecting a pure astrophysical signal, more or less pure astrophysical signal. So we can use also these neutrinos then to study the astrophysical sources that are producing them. To have an idea, this is the Neutrino Skymap that has been recently published by IceCube. And unfortunately, when using the neutrino data by themselves, there is no significant detection of single point sources, as I will mention soon. In this map, what they did was a blind search over 10 years of IceCube data. As mentioned, they didn't point out any high confidence single source detection. They tested also a list of extragalactic candidate neutrino emitters, and they found that the most significant hotspots in the sky are coincidence with a couple of sources that are reported here. In particular, this galaxy NGC 1068 is the one yielding the highest significance of about 3 sigma at the moment. And also they did some correlation testing sources in, for instance, the Northern Catalog, for which they found a significant correlation almost significant correlation at the level of 3.3 sigma. To summarize the status of art in terms of neutrinos, what we have learned so far is that there is neither individual neutrino source detected at high confidence nor source classes. There is also no significant clustering in the sky. So, for instance, if you look here, there is no sign of the galactic plane, right? What you said you would immediately notice in the Fermi map that I showed before. So there is no significant clustering in any direction, and as a matter of fact, the events are isotropically distributed. All this together, although they do not yield a confident detection, can be still very useful to understand the origin of these sources, of these neutrinos. In particular, what we can learn from it is that there is a hint to the cosmological origin of these neutrinos, and it also suggests a dominant extragalactic origin for most of them. Because, of course, otherwise we would see some clustering, right, if it was, for instance, of galactic origin. We don't, so more likely it's of extragalactic origin. Importantly, neutrinos are becoming a mature means to explore our universe. But, like the cosmic rays, unfortunately, their birthplaces still remain unknown. So, neutrinos by themselves are still not enough, let's say, to gain more insights into the origin of these particles. Indeed, one way that we can try to gain more insights is to use what I was mentioning earlier. So use the information that are provided by the neutrinos together with the cosmic rays and the gamma rays together. In particular, what people have been doing quite a lot in the recent years is to try to exploit the information gained at gamma rays along with the neutrinos. So basically cross-correlating the information in these two messengers. Here what we are looking at is in the background is the Fermi Skymap, just with a different color. And the circles overlaid are showing the neutrino, some of the neutrinos that have been detected with IceCube. Of course, one thing that might strike you is that the fact that these circles represent the localization of the neutrinos. And as you see, sometimes it's not that great. It can be pretty large. And this, of course, makes the scientific case more difficult to prove when we play with the correlation with these different particles. Anyhow, we can still attempt to do and gain some insight in this. And one of the most suitable approaches to do this is to focus on the neutrinos at their highest energies. This is because, as I mentioned earlier, the signal that we are detecting at the highest energies in neutrinos is more likely to be of cosmic origin. If we take the neutrinos at lower energies, you see that the fraction of these neutrinos that belong to the ground starts to be pretty overwhelming. So we can use them certainly, of course, but we need different techniques with respect to those that I will mention now. So focusing on the events at the highest energies, those that are more likely of being of cosmic origin, there have been different attempts in the literature of correlating them with gamma ray sources. And one of the first interesting hints in this direction was the correlation between Big Bird, which was a neutrino of one of the neutrinos of most energetic neutrinos detected by IceCube, with a gamma ray blazars detected by Fermi. Here is just for reference how it looked like. So this happened in 2014, and you see the color plots are showing the Fermi Skymap. This is a year before the neutrino arrival detection. And this is the same region of the sky, coincident, integrated over some months, coincident with the neutrino arrival. Big Bird, this 2 PV neutrino event, was detected in 2012 and had, unfortunately, a pretty large uncertainty in the position. So the uncertainty was about 16 degrees, and it's shown by this dashed line over here. So the neutrino will come from a region of the sky as big, but we do not know exactly from where. All the sources that are located basically in this region are plausible counterpart in principle of this neutrino. The important thing that made this neutrino quite interesting is the fact that the signalness, that means the likelihood of being of cosmic origin, was 1, almost 1. So that means that we are very confident that this neutrino was produced by some astrophysical process in our universe, and it's not background from Earth, from the sun, or whatever. This motivated then the search for a potential counterpart of this neutrino, and what we found together with collaborators was the fact that we noticed that there was this bright spot just at the border of the neutrino, which coincides with a Fermi-like blazar, PKS 1424-118 for reference. And interestingly, what we noticed was that this is before the neutrino and this is at the arrival time of the neutrino. You clearly see that the spot coincident with this blazar is much brighter. And that's brighter because at the arrival time of the neutrino, for some month over the neutrino arrival, the blazar underwent one of the major flaring activity ever recorded from this blazar, which is known, by the way, to be one of the most powerful by Fermi anyway, at gamma rays. For reference, you can also see here other bright spots in the sky. I hope you can see it. And this represents other blazars. And clearly you see that there is no major difference between the emission and gamma rays between these sources. So the fact that this source was much brighter at the time of the arrival of this neutrino, detection of this neutrino, made some collaborators think that there could be a connection between this blazar and the neutrino. or rather the other way around, so basically that the neutrino was produced during this major gamma ray flaring episode by the blazar. So this is all detailed in a paper, but just to give you straight to the point, unfortunately, of course, being the region of confidence of this neutrino pretty large, once we go to calculate the probability of association between these two sources, the source and the neutrino, what we found eventually is something that is not very significant. It's at the 2 sigma level. Just to give you an idea, there are 111 sources that were located within this region. Although this was not significant, however, in the paper that we have published, we show that blazars, in particular gamma ray blazars, are sources plausible to be originating neutrinos. And this is one of the first seminal papers, in my opinion, in this direction for the field. Since then, there have been many other works that have been published trying to address this case. And so, to date, most of the works have been using archival ice cube neutrino events. So, neutrino events that have been released only after some years that they were discovered. I would like, however, to point out the fact that since 2016, the Ice Cube collaboration started a program to release in real time the detection of these highly energetic neutrinos. Exactly for the fact that these neutrinos may be the most interesting one to be followed up at other wavelengths in simultaneous of when they are detected. The program now has been in place since quite some time. And so there have been several follow-ups that have been done. The most interesting one happened in 2017, when the Ice Cube collaboration reported the detection of a fairly well reconstructed neutrino. So the error on the position was, you see it 15 arc minute for the 15% containment radius. That, of course, it's not great for opticals, but for neutrino and gamma rays, it's just to give you a reference, it's pretty good. It's a pretty good localization that we can pretty use for doing astronomy. And another important thing was that the energy of neutrino was pretty high, and therefore the probability of this event of being of cosmic origin was quite significant. After the release of this alert, there has been an avalanche of observations that have been reported in all the wavelengths. And the most interesting one happened from the Fermi collaboration, which reported the detection of one gamma ray source that was located within the 90% error region of the neutrino. Again, the blue area defines the gamma ray Skymap in the location of the neutrino. And you see for this event, the reconstruction is represented by this circle, the 90% confidence region. And you immediately notice that in the center of this neutrino, there is only one bright spot. This bright spot coincides with the famous, nowadays famous blazar Texas 0506. The importance of this detection is resides mainly in two facts. The first one is that there is a unique gamma ray candidate found within this well-reconstructed neutrino event. And the second fact is the fact that the blazar was found to be in a flaring state. In a flaring state, that's what you can actually you can see from these plots here. This represents the light curve, the historical light curve for the blazar, recorded since the beginning of the Fermi operations. The upper plot defines the gamma rays, and you see this is the gamma ray flux detected from the source. And you see that the major flaring activity happened in coincidence with this time interval over here, which happens to be actually the time of the detection of this ice cube neutrino. Importantly, this high activity state of the source was persistent also in all other wavelengths. And here, for reference, I report only the optical band, where you see from these data points that there has been some variations before the neutrino detection, but the strongest activity of the source happens in coincidence again with this detection of the neutrino. So this motivates the collection of a large number of simultaneous observations, and it's thanks also to this large campaign that we were able to provide a pretty good, quite some modeling of the spectral energy distribution of the blazar. And here is what you see here. You see the two peaks that we were mentioning earlier. And this is the second peak, the Fermi-Lab data over here. And for the first time, we were able also to tentatively plot some information regarding the neutrino emission connected to electromagnetic emission. Of course, with the detection of only one event, we cannot really get much information, and already plotting this upper limit over here is not very reliable, actually. Anyhow, this is the first time that we were able to do it, and that's already a pretty good, important achievement for our field. So, of course, we pushed further the study, and we try to answer the question how likely it is to have a coincidence of an high-energy neutrino detected by IceCube with a gamma-ray source observed by Fermi-Lab in a flaring state. To go straight to the solution, we calculated that the post-trial chance coincident correlation between the two events is at the 3 sigma level, which indeed starts to be a threshold over which we may consider it a quite interesting event scientifically. Besides this, I wanted to mention also the fact that there's been a lot of efforts devoted also in trying to model the spectral energy distribution and the multimessenger information from the neutrino event that we collected in this campaign via several models. For instance, leptodonic models were used to explain the observation that had been obtained. I have to mention also another fact, which is quite interesting, and this is the fact that after the detection of this high-energy neutrino event, the IceCube collaboration went back to their data and tried to see if there was additional neutrino event positionally consistent with the same sky location of this high-energy neutrino. And quite surprisingly, they found actually several lower energy neutrino events, about 13, that are positionally consistent with the high energy event, neutrino event, and with, in turn, the Fermi-Lab blazar. This is more or less what you see here. This is a significance map for the low energy neutrino event, and the cross highlights the position in the sky of our Texas blazar. What we found, just to mention, is also the fact that these low energy neutrino events were clustered in time, and they were all detected over about 160 days interval between 2014 2015. The significance of this low energy emission was reported to be at the 3.5 sigma level by the IceCube collaboration. So this is quite interesting, and of course, it also prompts us to go back to our electromagnetic information and try to see if we can gain a bit more insights using also the information of this additional low energy neutrino event. But actually, this is where the trouble comes in. I say trouble, but actually it's probably even a more interesting story now. So you remember the plot that I was showing earlier, where we were looking at the electromagnetic emission in gamma rays and an optical from the blazar, and we were discussing the fact that the brightest emission was coincident with the detection of this high energy neutrino event. And this is also what motivated us to connect the bright state of the blazar with this single high energy neutrino event. On the other hand, when we look back to the historical data and we look to the simultaneous emission to the so-called neutrino flare, that is simply so the low energy neutrino event that will be detected in this couple of month interval. So when we do this, we notice that on the behavior at gamma rays as well in the other events, for instance here optical, the behavior of this blazar is completely different with respect to what we would expect if this correlation were true. So as a matter of fact, you see here the source is in a basically quiescent state or even low state compared to the historical emission. Of course, this prompts many questions and raises many doubts, but also motivates for further investigation of this type of events. As a take-home message, basically what we have found is that there is a significant different electromagnetic behavior during the time periods of the putative neutrino emission from these blazars. And this may be explained with different ways. For instance, there could be multiple neutrino emission regions that are acting in the blazar jet, and therefore they are depicted by different behaviors. Or there could be different neutrino physical processes that are originating the two different neutrino emission, and of course there is no reason why they should be behaving in the same way. But one thing stands, however, and that's the fact that the models that are producing neutrinos and gamma rays, they are required to be leptonic dominated at gamma rays. What this means is basically that the bulk of the gamma ray emission that we observe from these sources is of leptonic origin. And of course, you remember from the introduction before, leptonic means that there is no production of neutrinos involved. So just to summarize, this is still, in my opinion, pretty open for debate, whether this association of this neutrino flare could be actually true or not. So where do we stand now? Of course, we have acquired much more data since 2017, and we were able to also gain more insights into this potential gamma ray and neutrino connection. I report here just a couple of works, but there is really an avalanche of literature that should be given a note here. Among these, there is the now consistent picture over which the fluence of most individual blazar flares is too small to yield a substantial probability for detection of one or more neutrinos with IceCube. And also the fact that there is no absolute neutrino expectation for short-term blazar flares, because in this case, the expectation that we have for neutrino emission is negligible. Said in other words, short-term flares, for instance, in this case, the study was for days-lasting flares, are unlikely to yield a significant neutrino emission. So short-term flares are not good candidates, let's say, to find a correlation with the neutrinos. So what has been found so far is the fact that there is a possible contribution from individual flaring sources to IceCube neutrino flux. This cannot be excluded, of course, but what we find out from the observation so far is that this contribution has to be pretty modest. And in case it's more likely to happen for long-term flares. Long-term flares means like months flares, where the source has time to build up enough fluence and therefore build up probability for emitting neutrinos as well. Another very important thing to keep in mind now is the fact that the bright gamma ray blazars that we are looking at with, for instance, the Fermi are only the tip of the iceberg. So that means that the total observed gamma ray emission of all blazars is associated with the brightest individual object, only for a small fraction, because still the 70%, only 70% of the blazars' gamma ray emission has been resolved so far into point sources by the Fermi lat. That means there is a lot of sources that are there. They are emitting gamma rays, but we are not capable of resolving them individually. In terms of neutrino gamma ray correlation, what that means is that for any high energy neutrino event that we observe with IceCube, there will always remain a large probability of being associated with this population of fainter or even remote sources undetectable, which we cannot individually resolve. Another important thing besides this to keep in mind is that blazars can contribute only for up to 80% of the gamma ray diffuse flux. This also reflects in limits that have been derived by the IceCube collaboration. So they provide the stacking limits on the sources gamma ray blazars detected by Fermi, and they found out that this can contribute at most for about 30% of the diffuse neutrino flux detected by IceCube. So, okay, blazars, just to say, they are plausible sources for producing these neutrinos. However, they are certainly not the only answer to it. There must be other sources that are significantly contributed to some extent to the diffuse neutrino flux that is observed by IceCube. Therefore, we have to look to think also broadly what other sources are there and could be responsible for these neutrinos that we detect. In particular, among the alternatives, I mentioned just my favorites. So I like to think it this way. So we could go for the fainter but more numerous close-by populations. And among these, there would be, for instance, Starburst Galaxies, radio galaxies, AGN fast winds. Or there could be, for instance, transient sources such as GRB, supernovae, and tidal destruction events. Or on the other end, we could also think to alternatives such as the suggested dark gamma ray sources below 100 TeV. Dark stands for the fact that they are not observable as gamma rays because the gamma rays that are produced along with the neutrinos are absorbed within the source. And therefore they will cascade down, and the electromagnetic emission will eventually be observable in other wavelengths, especially lower energy with respect to gamma rays, such as the UV X-ray band. So these are the two most important alternatives to this main scenario that we have been discussing today. I just mention a bit more about these alternatives if I still have time. Maybe not much actually. So
no, but yes, please go ahead. Yes.
Okay.
Please go ahead.
Okay, thanks. Okay, so one of these alternatives is Starburst Galaxies. There have been some studies in this direction to try to connect the potential neutrino emission from this type of sources. As you know, Starburst Galaxy hosts a high rate of star formation and supernova explosion, and of course, these will foster the production of cosmic rays. The low-energy cosmic rays will remain magnetically confined within the environment and eventually will collide if the environment is dense enough. In this way, what happens is that the cosmic rays can be efficiently converted into pions, which, as we learned earlier, can in turn decay into high-energy neutrinos and photons. What we found out is that the power law neutrino spectra with high energy softening from cosmic ray leakage and or acceleration can be actually something that we observe and is consistent with the observations. Another alternative that I like to bring up is AGN-driven winds. So we have spoken about jets, relativistic jets, but jets are nothing but outflow material. And this material outflow is observed in AGN to be at different in different ranges and of different origin. In particular, what has become a pretty strong evidence nowadays is the fact that in several AGN there is the presence of these winds. Basically, they are not sort of jets, but they are not, how do you say, they have a broader cone, basically, or aperture cone, okay? And they are less energetic with respect to the blazar jets that we were talking before. Nevertheless, these winds are capable of producing shocks in the material and in turn also to accelerate particles at high energies and produce gamma rays and neutrinos according to the theoretical models. And an interesting perspective in this direction is the fact that one of the not significant but most significant spots in the neutrino sky detected by IceCube is this NGC 1068, which is for a source particularly complicated, but there is the hint that it could host one of these energetic outflows in its center. Although I have, of course, to mention that outflows in this case of NGC 1068 could not be the only solution, and there are papers, for instance, from Murad et al., who suggest other origin for the neutrino emission, putative neutrino emission from this source. Nevertheless, let me stress again that also in this case of alternatives, we are still stuck with the fact that also these sources that we are proposing nowadays, they can only account for less than 30% of the gamma ray background flux that we observe. And therefore, also in this case, they cannot be the dominant sources of the neutrino events that we observe from IceCube, unless they are opaque or for photons in the GV range, because otherwise simply we would have observed much higher flux, and we do not, so we can place a limit such that in this case. Finally, let me just deviate a bit from gamma rays, because I think it's important anyway to give a broader picture here. And in particular, these results came out 1-2 years ago, so it's pretty fresh and still open as well for debate, as well for improvement. And in particular, I'm referring to a couple of papers from Plavin et al., which now also was kind of confirmed by another group of et al. And what we did basically is try to study the correlation between these high energy events from IceCube with radio sources. In particular, they used a catalog of VLBI flux density limited sample of AGN. And what they find is quite interesting in my opinion. So they find that the AGN that are consistent with the IceCube events typically have a stronger parsec scale course with respect to the rest of the sample. And they find a post-trial probability of a chance coincidence of 0.2% level. So eventually, with the updated work that they have done so far, is that the final finding is that there is a tentative association between these radio bright blazars and IceCube neutrinos, which reaches now a level of significance of more than 4 sigma, which indeed starts to be quite interesting to further study. And briefly to mention, they also find, here maybe it's difficult to understand, but what they find also is that at the arrival times of the neutrinos are coincidence more or less with the stronger activity phase from the AGN that they are considering. So it's sort of the same story that we were discussing before. There could be some mechanism that accompany the enhanced electromagnetic emission, in this case radio, with the emission of neutrino events, also from this radio bright flat spectral radio quasar. Although I should also mention that actually from the theoretical point of view, according to what my colleagues told me, it's pretty difficult to explain the connection between these neutrinos and these sources. Let me go straight now to the final part of the final couple of slides. I just wanted to mention now the fact that we have been doing really great discoveries and great science so far, and hopefully the forthcoming decade will be similar. I report here just a couple of information regarding what to expect, hopefully. For instance, on the gamma ray side, there is this probe class mission that is currently being proposed to NASA, which is called Amigo. I leave just here the information if you're interested to read more. And of course, I didn't put a slide, but I'm sure you're familiar with the Cherenkov telescope array that is another important instrument in gamma rays that will be online hopefully very soon. On the neutrino side, there is a lot of development ongoing. I only talked about IceCube. IceCube is one of the main observatories online today. The future of IceCube hopefully will be IceCube Generation 2, which consists in a upgrade of the instrument in size, especially 10 times larger than the current telescope. And this will allow, of course, to improve much more the information that we detect with this telescope. Along with IceCube, there are several other observatories that are discussed or being constructed nowadays. One is Baikal, JVD, which is in Russia, and actually I think it's starting to be built right now. And on the European side, there is the CAME3net, which is you can think about it as the upgrade of Antares, which is the detector currently available. And this is already funded and is being constructed right now. And eventually, it will reach a volume size that is equiparable to IceCube, to the current size of IceCube. And the last one that I want to mention is P1, which has been very recently suggested. It's a team of German, Canadian scientists. And the idea is to build this telescope, this neutrino telescope in Lake Victoria in Canada. So I already completely went over my time, I think. So I will just leave here the summary. And thank you very much for the attention.
Okay, thank you very much for this great overview on high-energy neutrinos. It was a great talk. Thank you so much. We have a lot of questions here. Douglas, you can ask your question directly if you wish.
Okay, hi. Thanks for the talk. It was really interesting. So I just wanted to ask a few things about neutrinos because I really don't know anything about them. So I'm really curious about how do we determine the direction from which these neutrinos come from? If there are such a huge number of these particles passing through IceCube all the time, how can we actually say from which region of the sky these particular neutrinos are coming from?
Yeah, that's a great question, which I'll try to just briefly mention now. You should be able now to see my screen again, and what I wanted to show you is more or less how it works with the, for instance, IceCube detector. So of course, what we detect with the team detects with IceCube is not the neutrino event itself, right? What we detect is the interaction of the neutrino with, for instance, the ice. So eventually the neutrino that comes from the sun or from the source, as a physical object, in our case, the blazar, for instance, will travel through the universe, then will reach Earth, maybe go through the ice in Antarctica, and there it will hit an atom of water, for instance, let's say, or an atom. And when it does this, eventually it will generate a cascade of particles, among which muons, for instance, or pions. These particles have a special property in this case. The characteristic is that their velocity is higher than the speed of light in the ice. And as a matter of fact, they will create a Cherenkov cone, Cherenkov light. That is what the IceCube detector is capable of detecting, the Cherenkov light of these secondary particles that are traveling through the telescope. So once they detect this, what happens is this. These are basically the strings that I was mentioning before, and on each string there are several photomultipliers. So these photomultipliers have the capability of detecting the Cherenkov light, and therefore they record the information that some energy was deposited here. And doing such, they also can record the time at which it was detected, right? The energy was deposited. And in this way, we can build, you see here, early and late. We can also build the sort of direction over which the particle was traveling. So here it's the earlier time when it was first detected, and eventually this is the track when it was it went out. So there are different type of interactions in the detector. As you can see, it is not so well shaped, but nevertheless, the instrument, the software that they have built is capable also of reconstructing again the information regarding the direction in the sky and also the deposited energy by the particle, so that we know how energetic it was the original neutrino hitting the detector. Did I answer your question?
Yeah, you did. This is really interesting. Also, I had another one. Are there any theoretical correlations between the gamma ray and neutrino energies that we detect from these hadronic processes? Can we expect a particular correlation that we're looking for?
Yes, so we do. Actually, the answer is yes and no. It really depends on the type of source that we have. So physically speaking, no, the physics that we know working on Earth tells us that there is a correlation. I was mentioning earlier that in case of hadronic processes, we do expect that the neutrinos are accompanied by gamma rays. Okay, so this is simple physics. So we know that once you produce pions, you will produce both the neutrinos and the gamma rays. The problem is that afterwards, once these particles are created, we do not know much what happens to these particles. And for instance, there are many models in which the gamma rays may be produced maybe too close to the source. So what happens is that on the way out, while they propagate from the source, they may be absorbed because, as we know, for instance, there is high energy gamma rays can undergo pair production if they encounter on the way low energy photons, right? If that happens, we completely lose all the information from the gamma rays. So in that case, if the gamma rays are absorbed, we do not expect any correlation with the neutrinos. Nevertheless, we still can, of course, use this information because the energy of gamma rays is, of course, not lost. It's simply transferred, shifted into lower energies. So what you would expect in that case would be, for instance, UV or X-ray photons. So simply, we should keep an eye, besides of gamma rays, also in the other part of the electromagnetic spectrum, UV, for instance, and X-rays, according to the current theoretical models. Some, at least.
Okay, thank you. Thank you very much. This is really interesting to think about. Thanks.
You're welcome.
Okay, Rodrigo, you can go ahead.
Hi, Sara. Thank you for the fascinating presentation. My question is, what is your suspicion about why this particular blazar was strongly detected? Why the Texas blazar among the many thousands of blazars so far observed by Fermi? What is special about the Texas blazar, in your opinion?
Well, my opinion, so let's say in the opinion of the theoretician that I work with, in their opinion, it's not, actually. It's not so special. Actually, it's the contrary, because what they find when you try to model the emission from this blazar is the fact that it's an inefficient neutrino emitter. So that means that it's not among the brightest sources in neutrinos that you would expect. And therefore, it's really strange, let's say, that the first neutrino source that we have detected is not among the most efficient accelerators. Mm. Okay, so that's indeed, that's from the theoretical point of view. On the other hand, I mean, there is clearly also a lot that resides on chance. I mentioned, I tried to make the point earlier that the brightest sources that we observe at gamma rays are only the tip of the iceberg. So there is really a lot of more sources that could be causing these neutrinos. And therefore, it could be just by chance that we detected this blazar coincident with the neutrino, and that this neutrino was originated by chance by this specific source. I think it's my understanding that sooner or later we will have enough statistic, of course, to also say if there are other more correlation with this. But yeah, I'm pretty interested actually to keep my mind open, because I was mentioning, for instance, the results in the radio band, which are as well pretty attractive in my opinion, because it's very likely that in this neutrino astronomy story, we really have to think broadly, and we have to keep open mind over a large number of populations, that can be contributed just a bit, but all eventually significant. So yeah, this makes, of course, the work much more harder, but that's what we deal with.
Thank you.
Okay, Betty.
Hi, Sara. Very nice talk. And I'm Elizabeth Di Govia, by the way. And I have 2 comments and 1 question. One comment regards the blazar production and the candidates, right? And I'd like to comment that motivated by these findings and high variability in gamma rays, we have explored particle acceleration in blazar jets, in relativistic jets, in order to see if they could produce high energy cosmic rays that then could explain the gamma ray emission and the neutrino emission. And we have a couple of papers that we have just published in the IAG, it's 2021, 2 papers, where we explored this issue, where particles can be accelerated to 10 to 18, 19 electron volts in these relativistic jets by magnetic reconnection. So we did 3-dimensional MAGD, relativistic MAGD simulations. We injected test particles with, very low energies, smaller than the rest mass energies, and then they are efficiently accelerated by magnetic reconnection in these systems, because they, in these regions, they are magnetically dominated, and the acceleration. So we do believe that they have, there is more than energy enough to accelerate these particles, right? And also, now I have another comment with, by the way, these papers we produced with my student, Tania Medina Tarrejon, and Kadovakia postdoc. But anyways, I can send you these papers later on. The other comment regards the diffuse neutrino emission, because you discussed all the sources, the contributions from AGMs, from starbursts, etc. But what about the overall contribution from clusters of galaxies? And because these sources are immersed in clusters of galaxies. And also we have explored this issue doing cosmic ray propagation in cosmological simulations of clusters from redshift Z5 up to today. And what we could get the spectrum of neutrinos, and they contribute to a large fraction of the diffuse emission of ice cube. So these results are also we have just submitted to publication, and they are also already in the Astro PH. By the way, these are we did with my student Hussein. So this is also, and we got this. So really, I think this diffuse contribution could be some contribution from all the sources immersed in the clusters. Do you have any comments on this? I mean, regarding the clusters, I mean, as the source of the diffuse component of ice cube that is probably by us.
No, Elizabeth, thank you very much. I mean, of course, this is very important to bring up, both magnetic reconnection and as well the cluster and the other type of sources now. I mean, as I mentioned, it was just my selection of sources, population of sources that I provided. But thanks for bringing this up, because it's certainly important to keep in mind that was not complete. Typically, just to explain a bit the situation, typically we think, when we think about cosmic rays, we think about two types of main production mechanism. One is the reservoir model, in which you have, for instance, the galaxy clusters that you were mentioning, and the other one is the accelerators model, which is instead, for instance, the case of GRB or AGM. And I didn't touch at all the reservoir models here. Absolutely, I mean, you are right, and they are plausible origin, and very likely, as I mentioned, it's not unique, the solution, so it's very important, the work that you are doing, and I will certainly look back to those papers. And also I wanted to stress the fact that the magnetic reconnection is as well something that has become now pretty important to keep in mind as well. Because with shocks we cannot explain everything. For instance, there is the issue now, just to mention one, of short time variability that we detect at gamma rays. It's very difficult to explain those other observations that we are confident about already with just shocks. So there must be other mechanism, of course, working, and it's great the work that you are doing in trying this pioneering direction. Thanks a lot.
Yeah, we have been exploring reconnection, magnetic reconnection for several years. So yeah, definitely. So can I make another question? It is because, again, regarding the blazar candidates, so far the Texas source is, of course, but there are other candidates, right? And you mentioned some of them, but what among, because TSS is undisputable, let's say. I mean, we have this correlation in time and position of these events with the gamma rays. Hadronic contribution should be there, and we might have in mind that, although you said that the main contribution for gamma rays, it's possibly leptonic, and this is what Fermi, in the Fermi 100 GeV, probably this is leptonic. The tail in TeVs is probably hadronic, right? And then this is the one that we might expect to be correlated, the TeV that is protons that are decaying from pions and that are producing pions, and pions then we produce gammas and the necessary neutrinos, right? So I like to think about this, that it is a minor portion, because the protons, the hadronic part, will escape, so they will produce just a bit of gamma rays, but these gamma rays should be necessary enough to produce these flares, right? And so in this sense, that's why we are really pursuing and see if the gamma rays that are coming out from these sources, not right now we are calculating from this source using the reconnection model, right? So we are really doing this in order to try to reproduce the gamma ray emission of the source. But are there other convincing candidates that you, among blazars? Because I know that there are 3 or 4 more, but this is, I mean, what do you have to say about this? Are these confirmed? What are these sources?
Yeah, of course, as I mentioned, we are building now a bit of statistics. Oops, sorry. So I put in my backup slides just to give an idea of other sources. So we have recently teaser, recently it was in 2019 actually. Another bright blazar, PKS 1502 in this case, which was detected, found to be positionally consistent with another neutrino event of high energy. And this is just for reference the gamma ray emission and the radio emission from the source, and here is the arrival time of the neutrino. So basically, just to make it short, it arrived just after the main, this main long-standing flare in gamma rays. But as you see at radio, it's still pretty active. And this is probably also what's driven the significance in the other study by Clavin et al. So just to say, this is one other bright Fermi blazar that was detected coincident with a neutrino. Yeah, also this one, for this one, there was no statistical significance much relevant in this case. We are working now actually with Raniere on this source, which is another gamma ray blazar, an HSP that was found to be positionally consistent with an ice cube neutrino event, this I see over here. And I mean, potentially interesting in this source is the fact that there is some evidence for very high energy emission from the blazar. Unfortunately, we triggers a campaign to follow up the source with the Cherenkov telescopes, but they were not able to detect any significant emission. With Fermi, we find evidence for 100 GeV, more than 100 GeV photon. So that suggests that maybe the source can reach higher energies. But yeah, this is still a work in progress. And maybe, worth mentioning is this other source on which I've been working with the Antares collaboration. So again, it's another blazar for which there is a positionally consistent neutrino event. This is the gamma ray light curve, the black points from the source, and here is the arrival of the ice cube event. And potentially interesting is that in addition to this ice cube event, there is also a few tracks to few other neutrino events detected by Antares. And these are highlighted by these blue lines over here. But of course, you may notice that this is, we're talking about ER timescales. So of course, once we go to calculate the correlation, we do not get much significant level, unfortunately. There is a work that I've been doing with Anna Frankowiak, and has been published 1-2 years ago now, where we try to collect all the high energy neutrino attack events recently detected by IceCube, and correlated with Fermi-Lat blazars. Unfortunately, I do not have the slide here, but what we find basically is that it doesn't confirm, neither confute a correlation between the two samples. So just to say that clearly we are still behind with statistics probably to be able to make a step further. But I hope it will become soon, in my opinion, because IceCube has been both increasing the statistic, but also improving in some way the neutrino event, the way they reconstruct the neutrino event. So I'm optimistic, let's say, for the next years. I hope we will not have to wait for the next decade. Then it's on our job to do.
With these pandemics, one never knows. But anyways, thank you so much for the excellent review. And I will send you the paper.
Thanks. Yeah, I look forward.
Very welcome. Okay, thanks a lot.
Okay, Eduardo, you can ask your question.
Sorry, yeah. So my question is a bit out of the main point of the talk, but we talked so much about neutrino detection, and I saw myself wondering, do we have any technological path for the detection of the neutrinos of cosmological origin? Very, very low energy neutrinos.
Let me think. I think so. I'm not the right person to ask. But yeah, because what I pointed out in the talk were just the main instruments that are being built for this specific topic. But there is really a lot of activity in the neutrino field. For instance, there are GRAND, another instrument that is being built, which is a China-France instrument, I believe. And that as well is a very innovative instrument. As well, there are works ongoing in Germany, Ariane, I think it's the one, on which they are trying to use new techniques to detect neutrinos. And I'm pretty sure that among these other instruments that I'm not familiar with, there is also someone looking to probe the cosmological neutrinos. Because yeah, it's really a new kind of new field. I mean, it's old, but we are starting just now to be able to have the tools to study it. So yeah, sorry, I cannot really answer it straight, but I can provide the information if you like, certainly.
Thank you very much.
Well, Reinaldo, would you like to ask your question?
Yes, thanks for the very extremely clear talk. My question is more a curiosity. This new ongoing projects, these new detectors you showed by the end of your presentation, I'd like to know these advances in resolution, spatial resolution. They rely on some leap in the technology of the detectors, or rely on the same technology that exists for the IceCube, but different configurations of the detectors or different array?
Yeah, from my understanding, ChemTreeNet and IceCube, they rely mostly on getting bigger. They just increase the size of the detector. But as well, they also involve some developments hardware-wise on the hardware, and that will bring also improvements on the neutrino event reconstructions. Lake Baikal, the Russian one, I'm not much familiar as well. But from what I understood, it's as well based on the same technology. It's basically in the lake. The difference, basically, you have the IceCube is in the ice, okay, and ChemTreeNet is in the Mediterranean Sea. So you imagine the strings that are in the Mediterranean Sea simply. Instead, the Baikal experiment, that's in Russia in a lake. And same will be for P1 as well. They have these strings within the lake and the photomultipliers that will detect the particles. So my understanding is that, yeah, the main advantage will be probably just the size, but they do have some, of course, development as well on the hardware.
Thanks.
Okay, I have a question myself regarding the alternative model of these AGN winds. These winds are spherical, right? So would you have more chance of detectability given this, that you don't have the
yeah, it's not collimated.
Exactly, the collimation of the shot.
I missed the word as well before. So yeah, you are right. They are not collimated. That of course helps because they have a broader direction over which the particles are shooted. But on the other hand, since they are not collimated, they are less energetic.
Exactly. Yeah.
Yeah, but yes, certainly. I mean, they are basically not spherical, but we think they are cone shaped.
Okay.
In some cases, they kind of image them as well, and because you know, the AGN will have, besides the central black hole, then there is the accretion disk nearby, and then you have also the torus, this molecular dusty material that is surrounding it, and align on the same plane of rotational of the black hole, and that's maybe likely what's also giving this cone shape of to the material that is emitted. So yes, indeed, it will help that in that sense. Another caveat that I may mention of these winds, however, is that they might not be persistent. So in some cases, yeah, you have just a mechanism that is switched on and off in a pretty small amount of time, actually, compared to the lifetime of the AGN. So, of course, that means that you may have all AGNs having these winds, but not all these winds are active right now.
Yes, all the advantages you have with the bigger angle goes away because of this, actually. So
yeah, small time too, exactly. You have to be at the right time,
yes,
in the right place of the universe.
Yeah, maybe makes it even more difficult.
Yeah.
Okay, so is there any more questions? Juan, would you like to ask?
Yes, thank you for your talk. In your opinion, do you think that we are very limited by current data, or there is still many things to do with theoretical models? Or do you consider that, well, we are limited by current data and we have to wait for the next generation of detectors?
Yeah, I think the best thing of the Texas correlation with the neutrino is actually that triggered a lot of theoretical work, really a lot. And that helps a lot now because we have, according to the theoretician, of course, we have a better idea of what to look for, what features to look for. And that tells me that even if we do not have the best data available, the data that we would like to, we still can do a lot of science with this and important science. Because, for instance, of course, even if we do not have nowadays all the picture clear, this very tiny bit of information that we are getting are helping us in the way of building the generation telescopes, and also on where to put the funding from agency. And that's very important. It's not, something trivial to think about. So just to answer your question, whether it's data that is limiting us or theoretical models, I think it's more data probably. If we were to have better data, I'm pretty confident we would be able to pin down the electromagnetic emission that is accompanying these neutrinos in this case. Because, from the electromagnetic point of view, as you all probably know, we are living in the golden era. It's unimaginable what we have available nowadays. I could imagine more, of course, but I'm pretty happy with what we have. We can do really great science. For neutrinos, on the neutrino side, it's still very tricky because we do have events like these datasets, but most of this is buried into the background because they are at low energies. So yes, we could certainly do better. But we can try to exploit different techniques also. For instance, the stacking technique, right? If you have a very tiny signal that is present in many sources, you can just take it all together, stack the signal, and then get the brighter event. So that's a technique that I'm trying to use now with the neutrino data that are being made available. And I'm confident, said that in the next years we will have at least one other more discovery.
Okay, thank you very much.
Okay, so shall we close the YouTube transmission? Richard, please. Thank you.